Hi guys. In this video, we're going to start looking at 9.7. We're talking about inverses of matrices. So before we talk about inverses, I need to talk about identities. So an identity, for example, a multiplicative identity would be one specifically, but basically an identity is the number where if you multiply the two inverses together, that's the number that you get is the multiplicative identity. So for example, if I have 5 and 1 over 5 are inverses, if I multiply those together, I get 1. So 1 is my multiplicative identity. The other thing we know about the multiplicative identity is that if I multiply it by any number, it's not going to change that number. So 1 times 5 is still 5. It's not going to change. So that's true with any identity, is if I combine it with a number, it's not going to change that number. So for another example, the additive identity is 0. If I add two inverses together, so say 3 and -3, right, are inverses. If I add them together, I'm going to get 0. If I do 3 plus 0, it's not going to change. It's still going to be 3. So 0 is my additive identity. So with inverses, with matrices, we also have an identity, and that's going to look like this. It's going to depend on the size of the matrix, but it's always going to be square, and it's going to be a matrix that's all zeros except for the diagonal. So this diagonal here is going to be 1s, or this diagonal here is going to be 1s for a 3 by 3. So the things that make this an identity is if I multiply two inverses by each other, I'm going to get the identity, and that's in either order. Remember that this -1 just means inverse, so this is A times A inverse, and this is A inverse times A, and in either order, I'm going to get the identity. And also, if I do A times the identity, I'm still going to have A. It's not going to change. So that's the idea behind the multiplicative inverse of a matrix, right? It's going to be either of these matrices here, or it could be bigger, right? But it's just always going to have 1s on that diagonal from the upper left-hand corner to the lower right-hand corner. So looking at that, so in this example, it's just showing that I can multiply A times I, the identity, in either order. I can either do A times I or I times A, and I'm still going to get A at the end. It's not going to change, because that's the idea behind an identity. Also, if I multiply something by its inverse, I'm going to get the identity, and it doesn't matter which order. So if I want to show that two things are inverses, if I want to show that two matrices are inverses, I can multiply them together in either order, either A times B or B times A, and I'm going to get the identity in either one of those. I'm going to end up with the identity. Okay, so that's how we show if two things are inverses. If I multiply them together and I end up with the identity, then they're inverses, and I can do it in either order. All right. So the more complicated thing would be, then how do I find the inverse? So I know what the identity is, but how do I find an inverse? So there are multiple ways to do it. Essentially, you want your matrix A times something to equal your identity. So you can think of that as, okay, if I do the matrix multiplication here, I have my my row dot product with my columns, and that will give me these. And then I can say, okay, I know that this one needs to be 1, this one needs to equal 0, this needs to equal 0, this needs to equal 1. And I can turn that into a system of 4 equations and 4 unknowns. I can do that and it would work and I would get my identity. Sorry, my inverse. But there are easier ways to do this. So I want to talk about that. So this is the most kind of brute force way of figuring it out. There are easier ways, so let's talk about those. The next way I want to talk about is by using an augmented matrix where one side of your matrix is the original matrix and the other side is your identity. And basically what we're going to do in this strategy is that we're going to use that Gaussian elimination to get this into reduced row echelon form. So essentially, we're going to end up with, if you look down here, the identity on the left side, and then what ends up being on the right side is going to be the inverse. So you're going to go through that Gaussian elimination to get the identity on the left side. And it turns out that when you do that, what's on the right side ends up being your inverse. So in this one, they switched the rows, which you're allowed to do, and then they multiplied this bottom row by -2 and added it to row 1 and put that in row 1. So basically they made it so that this was -4 so that they could add them together and this number would be 1, which is what you want that number to be 1. There are multiple ways to do that, but that's the way that the book did it. And then we want to, once we get this 1, we need to get this to be 0. That's the next goal. So to get this to be 0, we multiply this top one by -2 and add, and put that in the second row. So that gives us this row. And then we want this to be 0. So since this is already -1, we can just add the 2 rows together and put that in row 1. So now we have the 0 here. And now we want this one to be +1, so we just multiply this whole row by -1 so that this will be positive. And now we have our identity on this side, so whatever ends up being on this side is going to be our inverse. So this is our inverse. And yeah, so that is one way to find the inverse of a 2x2 matrix. This strategy will work for any size matrix. And in the next video, I'll do an example with a 3x3 matrix. But there's one more way to do a 2x2 matrix that's even simpler, but this works for a 2x2 matrix specifically. So instead, we can find if we take our original matrix and we multiply it by 1 over something called the determinant, and we make B and C negative. So I'm going to kind of break that down. So first of all, let's talk about the determinant. So the determinant of a 2x2 matrix is AD minus BC. It's called the determinant, and basically it's this diagonal multiplied together minus this diagonal multiplied together. So see that it's AD minus BC. So it's the diagonal starting in the top left-hand corner multiplied together minus the diagonal starting in the top right-hand corner multiplied together. So that's the determinant. So we're going to be multiplying our matrix by 1 over that determinant. And we also have to make this diagonal negative when we do this. We have to make this diagonal negative. So in this example, our determinant is going to be 1 times -3, which is -3, minus -2 times 2, which is -4, so minus -4. So -3 minus -4 is 1. So our determinant is 1. So to find our inverse, we are going to multiply by 1 over 1, which is just 1, but I want to make sure we're remembering that it's 1 over the determinant, times 1 and -3 maintain their same sign, but the 2 and the -2 are going to change signs. Right? So this diagonal maintains its signs, this diagonal changes its signs. So we're going to multiply this by 1 over the determinant, and since it's just 1, oh, I forgot a thing. So this diagonal, sorry, backtrack a little bit. This diagonal changes its sign. This diagonal switches places. I forgot that. I apologize. That diagonal switches places. So we have -3 and 1 like this. So again, this diagonal changes sign, this diagonal switches places. So it's kind of a lot of pieces to remember, but if you have all your pieces, then this is definitely the fastest way to find the inverse of a 2x2 matrix specifically. So again, that's 1 over the determinant, which is multiplying this diagonal minus multiplying that diagonal. So 1 over the determinant times the original matrix, but you're changing the signs of this diagonal and changing the locations of this diagonal. And so then when we multiply that, 1 is just 1, so that's not going to change anything. So this is just going to be our inverse, which is the same answer we would have gotten with any of the other strategies that we looked at in this video. All right, I will see you in the next video.